In this video, we'll be talking about deletion. As you know, if a data structure you could only add things to, it wouldn't be nearly as useful as one that you can delete and insert to and do lookups. So deletion is a really important part of being able to understand how B-trees work. Alright, deletion is a lot like insertion in that there's common cases and there's less common cases that you both need to handle. Alright, so let's look at our previous tree here. We have a tree that's relatively filled out, and let's say we want to remove the key 59. Okay, so the first thing we need to do is we need to do a lookup. Okay, so what we're going to do is we're going to start from the top and we need to find the 59 key. 59 is bigger than 14, so we go down here. 59 is equal to 59 here, so we have to descend into this tree, and oh look, here's our 59. So how do we delete it? Well, we remove it from the leaf. And so this node becomes a node that just has a 79 in it. And the important thing to update is our internal node here as well, because what's the smallest thing now in this subtree? Well, it's a 79 now. So both you need to modify the leaf as well as possibly modify the parent nodes to let them know, oh, by the way, your smallest value now is a 79 instead of a 59 like it was before. Alright, so this is the easy case and the common case for doing deletion. However, there can be other edge cases that you want to think about. For instance, here we have wanting to delete a 5 here. So how do we delete a 5? Well, we start here. 5 is smaller than 14, so we go in here. 5 is equal to 5, so we go down here. I want to delete this 5. So what do I need to do? Well, I need to delete it from the leaf for sure. But then we have a problem. This leaf here is now under full, meaning it doesn't have half of L filled keys anymore. So what do we need to do? Well, we need to actually fix this problem. And so what we need to do is we need to figure out some way to either get rid of this leaf or to fill it at least halfway full. And so the way that you can fill it at least halfway full here is to do what's called adoption. It's when you adopt a value from one of your neighbors. So in this neighbor right here, this 1, 3, this is a full node, and it can afford to give up one of its keys, and it would still be okay because it's still at least half full. It's okay to give up this 3 to this node. And so if we move the 3 from here to here, and then we can update this internal node to say, hey, the smallest thing to the right of this is now a 3. Now we have a perfectly acceptable balanced B tree again, where each of the nodes is at least half full after this deletion. Now once again, the reason why we did this adoption, taking the 3 from here to here, is because we want to make sure that every node, every internal node, and every leaf node is at least half full, because if you don't ensure that, then your tree can become unbalanced. You lose a lot of the great properties that you would get from B trees. Alright, so let's do another deletion here. Let's say we have our tree here. We want to delete a 3. Well, how do I delete a 3? Well, I start at the 14. 3 is smaller than 14. 3 is equal to 3. I need to delete this 3 right here. Okay, so you have to remove it from the leaf, and so now you have this empty node. And then the question becomes, okay, what do we do now? Well, can we adopt from a neighbor? Can I take this 1 and move it over here? No, because then this leaf is under full as well. So there's no neighbor with surplus. There's no neighbor that can give me a key so that I don't have to be removed. So the only option is you have to delete this leaf. Okay, so we delete the leaf, but then the problem is this internal node has too few subtrees. You know, it's supposed to have at least 2 subtrees, because here our M is 3, so half of 3 is 1.5. We round up. Every internal node should have 2. So this internal node has too few subtrees. So what do we need to do? Well, we need to keep working at it. Here's the previous one. What we need to do is we actually need this guy to adopt a neighbor. This guy needs to take one of the children from its neighbors, and its child, and this neighbor right here, this guy can afford to give up one of its children. So you're going to move this leaf node from being attached to this internal node to being attached to this guy. Okay, so this internal node adopted a child from its neighbor. So now we have, and then we have to update the internal state of these internal nodes to say, okay, this guy now has to have a 14 because the smallest thing to the right of it is a 14. This guy needs to have everything shifted over by 1. So now its smallest thing to the right is an 89 here. And then this number up here also needs to be updated because the smallest thing to the right used to be a 14, used to be right here, but now it's this 79. So once again, this is another way that adoption can be used to balance the tree. And I guess it's a little bit strange in its syntax in that, you don't tend to think about, oh, my house is not full enough, so I'm going to steal one of the children from the neighbors so that I'd have at least a house half full of children. But that's how it works for B-trees. There's a lot of stuff in data structures that sounds really strange, and you might get put on a watch list if you said it like on a bus. But okay, so let's look at some other deletions. So if we have an internal node like here, and we want to delete a 1 from here, what do we need to do? Well, 1 is smaller than 79, 1 is smaller than 14. That means I need to delete this 1. This guy is now under full, so it needs to either adopt or be deleted. Hey, look, its neighbor, it can afford to give up a child, so you move the 14 over here, you update this internal node. Okay, so that's how deletion works. There's one other case we need to talk about, and we'll do that next. Let's say this is our B tree. Once again, this is a perfectly acceptable B tree. We have all of our nodes at least half full. We would say we want to delete a 26. So we start here, 26 is smaller than 79. We go in here, 26 is equal to 26, so we go over here. We want to delete this 26. So what do? We have to get rid of it from this leaf. And the problem is, okay, this leaf has too few keys, and it doesn't have anybody it can borrow from, right? This 14, it can't be afford to give up, or it would be too few as well. So we need to delete the leaf. So the leaf is gone. Oh gosh, this internal node is under full. Can we adopt anybody? No, this other internal node is also can't afford to give up its children. So we need to delete this internal node. And what we need to do is once we delete this internal node, we combine these two nodes together. Because we know this guy is under full and this guy is right at the edge, so that we can merge them together, and we have 79, 89, and this guy now has all of the children. The other thing we need to update is the node up above, the parent of the internal node. Now this internal node only has 1 child now, so it doesn't have any leaves. But now the problem is this root node is under full. This root node doesn't have as many children as it needs. It's supposed to be half full. It should have at least 2 when m is 3. So what do we have to do? Well, here's the previous tree again. What we need to do is we need to make the child here the new root, right? Because it's stupid to have a root that just has a pointer to the rest of the tree. We get rid of this root. Here's our new root. Here's our perfectly happy tree here. Okay? So that is how you handle deletion. Most of the time, you can solve matters by just deleting in the key, and you'll be fine. If you're deleting things in the leaf, you'll be fine. If the leaf gets too small, you adopt from your neighbors. If there's nobody to adopt from, you need to delete the leaf, and you need to take in the adjust your parent nodes. And sometimes, if your internal node gets too small, you need to either adopt from your internal node, or you need to merge those together. And if that goes all the way to the top, you may actually reduce the depth of the tree by getting rid of the old node and making its only child the new subtree. Alright, so I can describe what that is in text here again. The way that this works is you remove the key from the leaf. If it gets too small, you need to adopt. If adopt doesn't work, you need to delete that node and divide the keys among the neighbors. If your parent ends up with too small, it underflows as well. If the root ends up with only 1 child, make that child the new root of the tree, and so forth. Okay, multiple choice question time. Why will distributing the node's children and deleting the old leaf always work if adoption doesn't succeed? Okay, so let's examine these answers in their order of most wrong to least wrong. Okay, so first off, the last answer is silly. We can just cross that out right now. The third answer is also wrong. Adoption won't always work. Sometimes your neighbors won't have enough children to be able to offer you without underflowing themselves. So adoption is not guaranteed to work. Deleting the leaf will remove all of the children, guaranteeing the removal of the target. No, that's not the case, because once again, if you remove all of the children, then you're deleting more keys than just the one you want. So the correct answer here is actually the first one. If adoption failed, it means that you are underflowing, and it means your neighbor is at the minimum size. Your neighbor can't afford to give up anything. So if you add your less than half with your neighbor at half, you'll always be guaranteed to be able to fit all of the necessary subtrees and or keys together in the node by merging together with your neighbor. Okay, so The other thing that, just a couple more things in the slides, if an internal node ends up with fewer than half of the necessary subtrees, it underflows. It tries to adopt from a neighbor. If the borrowing or adopting doesn't work, then you need to delete that node and divide the subtrees between the neighbors. If the parent ends up with fewer than half, it underflows as well. And if the root node ends up with only one child, then the child is the new root of the tree. All right, so that is how deletion works in Btrees. So last slide here is talking about, actually not the very last slide, but now I want to talk a little bit broader. So when we're doing insertions, some insertions can be mildly expensive, where you have to do like splitting and propagating to keep the tree balanced. Most of the time insertion is very cheap because you just add it to the leaf, but sometimes that leaf gets too big and you have to do the sort of propagation up. Deletion can sometimes be very cheap, meaning you just delete it from the leaf, or relatively cheap, just doing a little adoption, which only changes a couple nodes, or it can be really expensive, where you have to do the propagation that goes all the way to the top. But propagation, the more expensive operation, is relatively rare if you have large M's and large L's. Okay, so in general, because you're using Btrees generally with large M's and large L's, these expensive operations occur very rarely. However, if you have a lot of insertions and deletions that you're constantly adding things to the index and removing things from the index over and over again, you can get thrashing, where your data structure is constantly propagating this insertion up and then propagating this deletion up and then propagating this insertion up, propagating this. So there's the possibility of getting bad performance if you have a Btree that's being constantly updated. So in general, that's why you tend to want to have indexing data that's not in flux as much, but sometimes that's unavoidable. The other thing to note is that M and L don't have to be very big to have a Btree that's very short. That's not so a kind of common sort of range of numbers for M and L are something like a nice power of 2, like 128. And so if you have a Btree with M and L of 128, if you have a Btree of just height 4, meaning you only have to go through 4 nodes to do your lookups, that Btree can hold 30 million items. So, and that's about the sort of scale of a relatively large database. So it means that if you want to do a lookup on a relatively large database, you only need to look at 4 places in memory to get there. Okay, so the other thing I want to talk about is specifically how Btrees are used as an index. So to make a Btree into a data structure that we can use for an index, we need to make a few small additions to how the Btree is structured. So the first thing is leaf nodes need to keep track of the values associated with each key. This is something I mentioned earlier. So in your particular leaf node, you say, okay, for this key, it has a particular value, like the row ID or something like that. And so there's a couple of different ways you can do that. You can achieve this with like a second list of values that's the same length as the number of keys in there, or each key can be a pair or something like that. That's not particularly challenging to make happen. The other thing that is a very common addition to Btrees that makes them B+ trees is that if you have each leaf having a pointer to the next leaf, it allows you to really easily move from one key to the next key to the next key to the next key to the next key, which is really useful for range lookups. So over here, there is this pointer right here that points at the next leaf. So if I wanted to get all the values between, I don't know, 8 and 80, well, so what I do is I do a lookup for 8. So 8 is smaller than 45, so I go over here. 8 is between 2 and 10, so I would start here. And then what I can basically do is run through the keys. So I have 10. And then I can follow this pointer to the next leaf, and then I return 45, 48, 56, follow this next leaf, 72, and then, oh, this is bigger than 80, I can stop. I can very easily run through my leaves to get everything within a particular range. And so that's really useful, and the nice thing is, especially if L is relatively large, you're only needing to access the necessary leaves to get your data. So this is, once again, a very efficient structure for both lookup and actually ranged lookups here as well.